Hello everyone. In this demonstration, we'll be analyzing and demodulating a recorded push-to-talk radio signal using GNU Radio Companion. My name is Robert and my partner is Lionel, and the goal of this demonstration is to recover the audio message from a captured signal file and show the process of bringing an RF signal down to baseband and then demodulating it. Here is the flow graph. The process starts on the left where we have a file block, and this contains the recorded file. Here you can see it's showing a path to the recorded file. This file represents a VHF push-to-talk transmission sample at a rate of 1.2 million samples per second. Up here we have the variable block. Well, this defines the variable sample rate. The variable sample rate has a value of 1.2 E6, which is equal to 1.2 megahertz per second. The signal from the file source is first visualized using these two blocks. Here we have the GUI sync and the GUI time sync. What these blocks do is that they display the spectrum and the waveform of the raw signal. Now I'll run the program so you can see what this looks like. This top one here is the time sync and this one here is the GUI sync. When you first view the spectrum, you'll notice that the main carrier signal, which is here, is offset from the center. And right now it's indicating an offset of, let's say, 526 kilohertz. To correct this offset, we will use a multiplier block together with a signal source block. What a signal source does is that it generates a cosine wave at a frequency of minus 256,000 kilohertz. Multiplying these two signals effectively mixes or shifts the incoming spectrum down by the same amount, bringing the carrier to 0 hertz, which is called baseband. Let me show you what this looks like. But before I do that, I have to enable the signal source, the multiplier block, and the GUI sync that shows the output. Now I'm going to run the program. As you can see here, the signal has been shifted to the center of the spectrum after the multiplication. Next, the output of the multiplier block goes through a low-pass filter. This filter removes unwanted high-frequency noise and any nearby channels. The filter has a cutoff of 10,000 Hertz and a transition width of 2,000 Hertz, which is appropriate for a narrowband FM signal. By limiting the bandwidth, we isolate just the portion of the spectrum that contains the actual audio information. I'll run the program to show you what this looks like. As you can see, this spectrum here represents the output of the low pass filter, and it shows that all other signals that are above 10,000 is actually isolated. After filtering, the signal enters the WBFM receiver block. This performs the FM demodulation. What it does, it converts the frequency variation of the baseband signal into a recoverable original voice audio. As you can see here, the quadrature rate, which is the input rate at which the data is coming in, is 1.2 E6. Now, the audio decimation is 25. Dividing 1.2 E6 divided by 25 will give you a output audio of about 48,000 kilohertz, which would match the frequency that the sound card on my computer can handle. Finally, the audio sync plays the recorded message to the computer speaker. Once the demodulator parameters and the frequency offset are set correctly, you can clearly hear the push-to-talk transmission. I'll run the program and show you.
Good job. You've successfully recovered the audio. Now make sure there is no static or noise in the signal.
Thank you for watching our demonstration. This concludes the analysis and recovery of a push-to-talk radio signal using GNU Radio Companion.